Good morning, good afternoon, and good evening, wherever you are. Today I want to do Euclidean geometry. I want to do a summary of the theorems that we learn in grade 12. And in another video, I'll also do the proofs. But now I just want us to have a summary of those 9 theorems. So now we have 9 theorems that we get questioned on in an exam in terms of grade 11 Euclidean geometry. And for those who are doing grade 12, you will see that in your grade 12 paper there is more grade 11 Euclidean geometry in terms of marks than grade 12 Euclidean geometry. So it's quite important for you to understand these theorems and know them. So before we prove these theorems, I believe that it's good that we know them, and the best way to know them in this case is to use these groups that I will now explain. So there's 9 theorems. We are going to divide them into groups of 3, so it's going to be 3 by 3, which gives us 9 theorems. And there's also a 4th group which I will also talk about. It's also quite important, because if you don't understand the 4th group, you may not be able to answer any of these questions in an exam. So let us start. So I spoke about 3 by 3, okay, which is equals to 9. So now this is telling me that I am going to have 3 groups, and each group is going to have 3 each. That's why now I have 3 groups. So group 1 is going to be the theorems that have to do with the centers. So group 1 is my centers, and group 2 is going to be the cyclic quads. So I'll just write CQ for cyclic quads. And then now we want to also look at group 3. Group 3, you've guessed by now that it has to do with the tangents. So those are the groups: group 1, group 2, group 3. Group 1 is centers, group 2 is cyclic quadrilaterals, and group 3 is the tangents. So in each group we are going to find 3. In each group we are going to find 3. Now let us just discuss the groups in detail. So now I have my group 1, which we already know that it is the centers. So these are the center theorems. Now the first one in group 1 of the centers is the line from the center. So line from center. Line from center. And basically with line from center you have your circle, you have your chord and line that is drawn from the center. Okay, and now there's 2 ways to prove this particular theorem, and this is why I'm not going to do any marks. But now the line from the center can be perpendicular to the chord, or it's also going to bisect the chord. So it's perpendicular to the chord, it's also going to bisect the chord. So it's perpendicular to the chord, also going to bisect the chord. And now in an exam situation, there's two ways you can be asked to prove this. So it's the only theorem that has two proofs. So the first proof you can prove using congruency, you can prove using RHS, or you can prove the second one. Can prove the second one using side. So yes, we are going to do this proof when I'm done with the summary in a different video. So line from center, starts from the center, goes to the chord, it's perpendicular and it bisects that chord. And we'll explain the two proofs later on, but we prove this theorem using congruency. And the second theorem in terms of the centers in group 1, it is angle at the center. Angle at center. Angle at the center. Angle at the center is twice angle at the circumference. Angle at the center is twice angle at the circumference. So I'll just write angle at the center, and now you would have your center, and so what is being said here is that basically the angle here at the center is 2 times angle at the circumference. So if this angle is 2x, that will become 2x. This angle is 10, this would become 20. Okay. If this angle is 50, this would become 100. Now this one is you are also required to prove in an exam situation. We'll do also when we are doing the proof of the first theorem in group 1. We'll also do that proof. Okay, so this one has other ways it can materialize. So you can still be having your angle at the center like that. Going to be having your angle at the center like that, but now you're looking at the reflex angle here. That reflex angle outside there is going to be 2x, meaning that this angle here is going to be x. So you have angle at the center twice angle at the circumference, then you have this reflex here angle twice angle at the center here is twice angle at the circumference. There's other ways that we can look at it. We can also have basically still have your angle at the center. Is going to be now the angle at the center is going to be twice angle at the circumference there. So this angle here would be 2x and that angle there would be x. Hopefully you can write that one down, but it's 2x and that angle there is x. And one that I see some ignoring, you would have angle at the center like this. So this is still angle at the center is twice angle at the circumference. So now it's going via the diameter, whereby the angle at the center here, which is 2x, would be twice angle at the circumference. So 4 possible ways this theorem can be asked in an exam situation. So just be aware of those. But we are going to use exterior angle. We are going to use the exterior angle. We are going to use exterior angle to prove this one. Exterior angle of a triangle. The third theorem in terms of the centers, it's now going to be angle in a semicircle. Angle in a semicircle. Angle in half a circle. Basically, angle in a semicircle comes from angle at the center. It's twice angle at the circumference. And I can just show you that quickly. You're not required to know how to prove this one in an exam situation, but I think it's good if you know why angle at the center is 90 degrees. So angle at the center means that you have, in this case, we are going to use angle at the center to show why angle in a semicircle is 90 degrees. So angle in a semicircle, you have a diameter which cuts the circle into two equal halves. That's why now it's a semi. It's just half. So it's now half circle, half circle. So now we are seeing that the angle in a semicircle is equal to 90 degrees. So the reason why that is because you have 180 degrees here, because you have angle on a straight line. So you have that angle on a straight line, and then you can say angle at the center is twice angle at the circumference. Now remember I said if this one is 20, this one would be 40, this one is 2x, that one is x. So even the same thing here, you have angle at the center is supposed to be twice angle at the circumference. So this one will become 90 degrees. It will become 90 degrees. That is why you have angle at the center is twice angle at the circumference, giving you angle in a semicircle. But we just need to remember that angle in a semicircle is equal to 90 degrees. And that's a basic summary of group 1. We're dealing with the centers. Group 1 dealing with the centers. This one, there's two ways to prove it, and it can be asked in an exam, any of the two ways. This one, there is one way to prove it. So there's in group 1, the centers, you are looking at 3 proofs that you need to know. 3 proofs that you need to know. Now, we move on to group 2 quickly. We don't want to make the video too long. Group 2, remember I said I'm dealing with cyclic quads. Cyclic quadrilaterals. Cyclic quads. Now a cyclic quad is supposed to have all 4 points on the circumference of the circle. So that's why it's a cyclic quad. So you have A, which is opposite angles of a cyclic quad. Opposite angles of cyclic quad, we are going to be having a circle and a cyclic quad. And a cyclic quad. All 4 points must be on the circumference. So we have A, B, C, and D. Now, this one you are also required to prove. You'll use your center to prove this theorem, and you are also going to use the proof from the centers. Angle at the center is going to be used to prove this one. So you see, in geometry you are always referring to what we learned before. Like we learned congruency in grade 9, grade 8, grade 9, and then now we use congruency to prove theorems in grade 11. We also learn exterior angle in grade 8, grade 9. also in grade 10. So these theorems come from grade 8, grade 9, and grade 10. Congruency, the two types of congruency that we are using here, and the exterior angle of a triangle. These are from previous grades, so we use them to prove these two theorems. Now we use angle at the center to prove angle in a semicircle. Now we are going to use angle at the center to prove opposite angles of a cyclic quad, which I have mentioned that I'm going to do a separate video just discussing the proofs, showing you how to prove all these theorems. And so we know that here A plus C are equal to 180 degrees, and B plus D also equal to 180 degrees. Both pairs equal to 180 degrees. So you can prove, if you want to, you can prove that A plus C equals to 90 degrees, or you can prove that B plus D equal to 90 degrees. Does not matter which one you want to start with. We'll do the proof. But now remember, the proof, we are going to be using the angle at center. We are going to be using the angle at center, which is the theorem we already have there in group 1. And the next one is the exterior angle of a cyclic quad. Exterior angle of a cyclic quadrilateral. Okay, exterior angle of a cyclic quadrilateral. Now, exterior angle of a cyclic quadrilateral, we cannot prove it or do it without understanding firstly the opposite angles of a cyclic quad are supplementary, or they add up to 180 degrees. So now you have again your circle. I'll just redraw something similar to the previous one. You have A, B, C, D, and so this one I'll name C1 and C2. So what we are saying is that this angle C2, this angle C2, the one here on the outside, is going to be equal to the angle there. Those angles there are equal to each other. Okay, so there's a very basic reason for that. Once you understand that opposite angles of a cyclic quad, they are supplementary, they add up to 180, then you'll see that A plus C1 also add up to 180, but C1 and C2 also add up to 180 because now you have angles on a straight line. So now, since C1 and C2 add up to 180, and A plus C2 also add up to 180, that means that C2 is now equal to A. Very, very simple to understand that one. And I can show you quickly why. You have angle A plus C1 equals to 180 degrees. We know that opposite angles of a cyclic quad are supplementary. But you also have C1 plus C2 equal to 180 degrees. So you see they are both equal to 180. So I can just have A plus C1 equals to C1 plus C2. So you'll see once I move C1 to the other side, it's going to be negative C1 and cancels with this one. So now A is equals to C2. So that's why exterior angle of a cyclic quad is equals to the opposite interior angle. And the last one in group 2 in terms of cyclic quads is now the the angles in the same segment. Angles in same segment. Angles in the same segment. Now some people may argue this is not a cyclic quad theorem, whatnot. We can also make the argument that we have all 4 points on the circumference of the circle, therefore it's a cyclic quad. Some people like to say no, it's a shape of a bow tie. It's not exactly a cyclic quad, but it fits the definition of a cyclic quad, whereas you have 4 points on the circumference of the circle. So yeah, this theorem you can also prove using angle at the center is twice angle at the circumference. So it's quite important to understand angle at the center, because now we have because of angle at the center is twice angle at the circumference, we can prove angle in a semicircle, we can prove opposite angles of a cyclic quad, we can also prove exterior angle of a cyclic quad from this one, which was proved using angle at the center is twice angle at the circumference. So that's the important part there. So even this angle here, you can this theorem here you can prove using exterior. You can prove using angle at the center is twice angle at the circumference. It's quite simple, but I won't show it too much. What you would need to do, basically, you would need to have your center. So I'll have my center right there, and then you just join center to. You just join your center there to one of those. So you have your center there. You join this center to one of the chords. So you see now you have that angle at the center there. It's going to be twice the angle there, and it's also going to be twice that angle there. So now that's why those two angles in the same segment are equal. So you see angle at the center is quite important, because you can now prove those with angle at the center. And not required for exam purposes. So with this one, you can also have other variations, because you are basically having this chord here. I'll call it chord AB is subtending that angle and that angle. So you have chord AB subtending this angle and subtending that angle there. That makes it equal via angle at the center. You can also have a variation of this particular theorem, whereby now you can have something like this, whereby now those two chords are equal. If those two chords are equal, meaning that those angles there, they're also going to be equal, because now we had chord AB subtending those angles. That means this chord, since it's equal to that chord, is subtending the same angles or equal angles. So with this one, you can use angles subtended by equal chords. Is the reason for using this particular theorem. So now, just to recap, we have centers there. There's 3 of them. You can pause the video and write them down, look at them carefully, and we'll still prove those 2 theorems. And there's 2 ways to prove this one. We'll also show that there's one way that will do, and we also need to know how to prove opposite angles of a cyclic quad are supplementary in an exam situation. These other ones we don't really need to know how to prove, but we must know them, know how to use them. So now let us move on to group 3. So now group 3, we say that group 3 has to do with the tangents. Group 3 is now the tangents. The first one there is going to be the tan radius. The tan radius theorem. So you have your circle, you have your radius, you have your tangent. So circle, radius and tangent, so forms an angle of 90 degrees there. So it forms an angle of 90 degrees. So the proof for this one is more varsity level. Use something called contradiction to prove it. We'll not get into that to save time. But yeah, this is the tan radius theorem. It has to do with the tangent and the radius that are perpendicular to each other. And the second one there, we can prove it using the tan radius theorem. And this one is tangents drawn from the same point. Tangents from the same point. Tangents that are drawn from the same point. So imagine you have a circle and you have this point here. You draw a tangent from that point to the circle. You draw another tangent from that point to the circle. So that is the point of contact. That is the point of contact. Those lines, they are going to be equal. So tangents from the same points are equal. You can prove this using congruency. So you need to have a center first of all. Then after having your center, you would need to construct a radius and another radius this way. So we already know, and you need to construct that line as well there, from the center to that point that you draw from your tangents. So we already know that this one is 90 degrees because of tan radius theorem. We've just shown that it's 90 degrees. This one is also 90 degrees. It's tan radius theorem. So what do you have here? You have your 90 degrees. You have the radii, which is equal. The radii is equal, and you have a common side, which is also the hypotenuse. So you've proved RHS. That's why now those two are now equal. I won't get into that too much. It's just that I will say point P. I'll name this one A. I'll name this one B. I'll say that PA is equals to PB. And we use RHS to prove this one. RHS to prove this one. If you want me to write down the proof for you, indicate, so that in the next video when I'm doing the proofs, remember in group 1 I have 3 proofs. I must prove angle line from center. I must prove it 2 ways, and I must also prove angle at the center is twice angle at the circumference. And then in group 2 I must now prove that opposite angles of a cyclic quad are supplementary. So I'm going to show that in the video, because those are for exam purposes. This one is not for exam purposes, the proof, but I can show you if you indicate in the comments that you want me to show you the formal proof. I've already discussed it, but maybe just to write it down how you would do it. Now the last one, we all know that this is the tan chord theorem. Tan chord theorem. This is the tan chord theorem. So now the tan chord theorem you are also required to prove in an exam situation. Okay, tan chord theorem you are also required to prove in an exam situation. So your tan chord theorem, remember now we're just dealing with tangents here. It's tangents, hence it's called tan chord. So you'd have a chord, another chord there. So the angle between the tangent and the chord is equal to the angle in the alternate segment. So So the angle between the tangent and the chord is equals to the angle in the alternate segment. So now the same thing applies for those two angles there. They are equal. That's tan chord theorem. There's two ways to prove tan chord theorem. I'm also going to do those two ways. You will choose which one is better for you in that video. But now I can prove this theorem using diameter. If I construct the diameter, that is the first way I can prove it, which is what most people are used to. Or I can prove this theorem using radii. I can prove this theorem by constructing radii. So, two ways to prove tan chord theorem. Both are quite simple. I like both of them. But we use a lot of other theorems that we've already proved. For example, when you use radii, you are also going to use angle at the center is twice angle at the circumference to prove the tan chord theorem. So that's group 3 with the tangents. And I also spoke about group 4. Now remember, we said there is 9 of them, which is 3 groups each. So in each group you have 3, which makes it 3 by 3, then it's 9. And yes, I spoke about them and said, okay, we have got, I spoke about them and said, okay, we've got 3 times 3, which is 3 groups, 3 each. Group 1 is the centers, I've already shown you. Group 2 is the cyclic quads, I've already shown you those. And then group 3 is the tangents. We just discussed those. So, and you need to know 2 here in terms of to proof, but the line from center, there's 2 ways it can be asked. So there's basically 3 proofs in this one that you must know for exam purposes. And there's 1 in here that you must know for exam purposes. Then there's 1 in here that you must also know for exam purposes. So all in all, there's the proofs that you are looking to prove. There is 5 of them. 5 of them, because the line from center, they can be asked in 2 different ways. You need to know the proof, and angular opposite angle of a cyclic quad are supplementary. You need to know how to prove, and tan chord theorem you need to know how to prove. And there's 2 ways of knowing how to prove tan chord theorem. It's just 2 ways. They are not going to ask it in 2 different ways, but it's just 2 ways of proving that one. So now I just want to quickly speak about the fourth group very quickly. Fourth group, we all know this one is parallel lines. We learned it long ago in grade 8 and in grade 9. So it's important because without parallel lines, then the Euclidean geometry becomes short. There's not much you can do, but you must understand parallel lines very well. And a lot of people use this concept of fun to try and remember these parallel lines. So now the F will obviously now indicate the corresponding angles, and the U would now indicate co-interior angles. And the N, sometimes you see it as a Z. So I also like to write not only fun but fuzz, okay, because it can also be in that Z shape. Even the U, you can turn it upside down, it can look like an N. And this F can also face the other way, or face upside down. So, but I think you get the main concept. You've been doing this for many years now, and I'm just giving you that summary to say it's so important, the parallel lines, that we have to include it as the fourth group, because there's so many questions that contain parallel lines. In fact, I don't think that you'll find paper 2, grade 11, grade 12 paper without parallel lines. I don't think that would happen. So it's important to understand these parallel lines. And so obviously the N or the Z is alternate angles. It's the alternate angles. So I'll leave this video here. Later on I will do the video for the proofs, the 5 proofs that I've just discussed, and I'll make the video short in terms of the proofs. And yeah, leave comments in the comment section. If you have not already subscribed, please subscribe and turn on that notification bell, so that whenever I drop new explanations on this channel, you are able to get those videos and learn with me together. So thank you very much.